your time. Hopefully I made a lot of progress. Enrique knows me since the first time I ever figured out what differential geometry was. Let's see if I made a little bit of progress. So I went on after working with Enrique to work with Finsler metrics with Professor Shen at Purdue University. And so my outline for this talk is going to be to introduce a little bit of Finsler spaces with basic definitions. I'll try to keep an approach that's parallel to Riemannian geometry because I know it's much more popular and people know a lot more of. And this approach, having this parallel, usually helps us understand a little bit more of the dynamics of Finsler spaces. And I think it's going to be beneficial and a little bit more light. Then I'm going to go on to talk of some famous families of metrics, of Finsler metrics, that appear very naturally in different contexts. And then I'm going to talk about the notion of work product for Finsler metrics. And we have basically two different types of approaches. One given by Cosma, Peter, and Varga back in 2001, and one that was introduced by Professor Shen and his collaborators in 2018. And I made a little bit of tweaks in that definition to consider another type of warping, basically. So he introduced a very specific type of warping, and I studied another type of warping. We're going to get there. And then at the end, I'm going to leave you with a few possible directions that still need to be studied in this and open for your questions. So let's begin. What is a Finsler space, right? So we'll begin with a smooth manifold finite dimension, so dimension n. And we're going to take a function over the tangent bundle that's positive, and it's going to define a Finsler metric on M if it is infinity on the tangent bundle, except at the zero section. So we're called the slit tangent bundle. If it is positively homogeneous of degree 1 on Y, so on the vector and the tangent vectors. And the symmetric linear form for each non-zero tangent vector defined by the derivative is positive definite, and we call this condition strong convexity. So if we have local coordinates over our manifold, we can induce the coordinates over the tangent bundle, and then we can write coordinates for the symmetric bilinear form. And this gives us the Hessian matrix of x squared. So strong convexity is just saying that this Hessian has to be positive definite, right? The motivation of this is usually because Finsler geometry started by a geometric approach to calculus of variations. So you want to measure the length of a curve in the most general form possible. Regularity you have to have because you're talking about differential geometry and smooth manifold. Then positive homogeneity is about the distance, the measure of the length of your curves being independent of reparametrization, also of the speed of the curve. And then strong convexity in the calculus of variations is related to the existence of maxima, which is pretty cool. And then what you end up with, so let me stop here. I'll talk a little bit later. What I'm going to talk about now is that if you look for each point, so fixed x, what you have, it's going to be called a Minkowski norm over your tangent space, right? So at each point, what you have is a Minkowski norm. Instead of an inner product, you have a Minkowski norm. So that's what I was going to say. You have this smooth varying family of Minkowski norms over your manifold, instead of a smooth varying family of inner products, as in the Riemannian case. Okay, So homogeneity, we want to use Euler's function theorem, and then this gives.
Excuse me.
Go ahead.
Could you go to the previous slide, please?
Yes.
This f squared is a typo or is something important?
No, it's just the square root of the function.
Okay, great. Thank you.
You take half of f squared.
Yeah, I understand. Thank you.
So we take Euler's theorem to work with the homogeneity, and we can write f as the sum. I'm using Einstein's notation here, so sum in I. The same thing for second derivatives, and then that's going to be 0. So f is homogeneous of degree 1. Then you have this reiteration of Euler's theorem, which means that f squared being homogeneous of degree 2, which is the one that we have on the definition of the GIs. So you can get f back from the GIs, right? Which looks very similar to the Riemannian, except that our GIJs have a dependence on y. If they only have a dependence on x, then that's going to reduce to a family of inner products on your tangent space, and you have a Riemannian metric. But if you have the dependence on y, that's not an inner product on each of your tangent space. What you do to study this object is you go to the pullback vector bundle over the slit tangent bundle. So there, this GIJs, DXI, DXJs make sense. And it's what's called the fundamental tensor related to your Finsler metric. Similarly, you can take another derivative, and that's going to define the Cartan tensor over the tangent bundle, the slit tangent bundle. So on the pullback vector bundle.
Can I ask a question?
Yes, go ahead.
Do you then think you could classify Finsler metrics by the holonomy of the induced metric on the pullback bundle?
Perhaps.
Because you've told me in the past that classifying Finsler metrics by the holonomy makes no sense, and that's a ridiculous question to start with. However, it does induce a genuine Riemannian metric on the pullback, so maybe
yes.
This is something we could look at.
But then a problem is over your manifold, you can have more than one thing. So you're going to have a quotient of some sort that descends to your manifold in the same way. You're having a coarser vision of classification than you might want.
Well, can you say that two Finsler metrics are not the same if their induced Riemannian metrics have different holonomy? Say.
That's something I don't know.
Okay.
But it's an interesting question.
Okay, no.
Okay. And then Cartan tensor is the first non-Riemannian quantity that we come across with. Because if you look, the CIJKs are just, can be written as a derivative in YK of these GIJs. And then that all coefficients of the Cartan tensor being 0 means that your GIJs are independent of Y and then descend to that Riemannian metric. They simplify to that Riemannian metric, right? So we're on this setting where we have to go to this slit tangent bundle. And on the slit tangent bundle, we have a very important globally defined vector field that's called the spray induced by the Finsler metric. And this GI, so are the spray coefficients, and they can be simply computed through the derivatives of f squared. You may have globally defined vector fields on a space that are actually not induced by a metric, by a Finsler metric. So you may have this vector field that has some special nice properties. and they may not come from a Finsler metric. And then the study of this spray manifolds is a more general possibility in geometry, actually, and it's another field, basically. And the key fact here is that if you project the integral curves of G to your manifold, that will coincide precisely with the geodesics of your manifold. I'm not gonna prove that because we need some more definitions. And another interesting quantity that I can introduce here is the nonlinear connection, which I'm going to look at those derivatives of the coefficients of GIs, so how they change with respect to YJs. Why they are called a nonlinear connection? We have to go back and remember that we're studying tensors over the pullback bundle. So if I'm looking at the tangent bundle of the slit tangent bundle, I can describe a local frame as just the partial derivatives. However, if I change coordinates on my manifolds, the transformation of this local frame is not natural. And the same for the cotangent bundle over the slit tangent bundle. So what we do is we change the partials with respect to xi's to these deltas that has an account with this nij's, and the same for the cotangent, but then for the delta yi's. And so if I take local basis composed by these deltas and partials for the tangent, and then dxi's and delta yi's for the cotangent, they'll transform naturally with the change of coordinates over the manifold. Which means basically that I'm splitting the tangent bundle over Tm minus the zero section as this horizontal and vertical spaces, or subspaces, right? Which are generated by the deltas, and by the deltas, delta xi's, or partials, partial yi's. And that's what gives rise to this Edisman connection. So that splitting, that Edisman connection is because you have the splitting, and the splitting is a direct consequence of having these coefficients and ij's, which are hence called nonlinear connection, right? And we came across the definition of a connection. If you want to do differential geometry, you have to have that. And the same way as the fundamental tensor and the Churn tensor are over the pullback bundle, the connection, a affine connection for Finsler manifold is also going to be defined over the pullback. The most famous one is the Churn connection that is characterized by structural equations being torsion-free and almost G compatible. So almost, because it's going to have this dependence with the Churn tensor on the right side. And basically the way to prove this is similar to the Riemannian case. So the connection one forms will have a very similar form to the Christoffel symbols in Riemannian geometry, except that instead of partials, we now have exactly those deltas that we defined, right? Can a connection on a Finsler manifold be both torsion-free and G-compatible? Only if your metric is Riemannian, right? Because only if theCijk's disappear. And can you have, in some sense, this connection is not going to be unique. It's not going to be the favorite one. So you have other connections that you can define on this pullback bundle. For example, we have the Churn connection. That's going to have connection forms given by the same one as the Churn plus this CIJKs, the CIs here are the up with the GIJs, so the inverse, right? You pull up the index. And you also, in the Churn connection, it's going to be torsion-free, but not metric compatible. Sorry, it's the other way around. It's going to have torsion, but it is metric compatible. And you also have the Berwald connection, which is, as the Churn connection, torsion-free, but not metric compatible. And the compatibility here, you're going to have an extra term. So you have this two CIJKs, delta YKs, plus some other term in there. And then which connection can I use? Depends on the problem you're working with. So Berwald connection, although they seem more complicated than the Churn connection, they work well for metrics with constant curvature. Okay, and you may have other connections as well. I'm talking about these three because they're the three most famous and most used ones. Now that we have a connection, we have curvature 2 forms related to that affine connection. And since they're living in this pullback bundle, we can generically expand them with this horizontal components, which are the R's, horizontal-vertical, which are the P's, and vertical-vertical, which are the Q's. And then the tensors generated are PQ, are exactly called HH, HV, and VV curvature tensors. For the Churn connection, if I remember correctly, the Q's are 0, and then you have R and P, but it's not important. Once you have this, we're going to define a contracted tensor, RIK, by contracting with Y for each point on the slit tangent bundle. And then we can define this Riemann curvature as now a family of transformations over your tangent space. So for which Y, you have a linear transformation over your tangent space. And then the flag curvature you can define from this Riemann curvature. And it is called a flag curvature because it depends on a choice of Y. So for each, it is the generalization for the sectional curvature. So for each plane, for each tangent plane on your space, you need to have this pole, so the space vector that's going to define which of these transformations in the family of transformations of the Riemann curvature you're choosing. In an intuitive way, you're thinking about, it's like you have a base direction that's your observation. So you measure depending on the direction you're observing. And then you take the Ricci curvature to be the trace of this Riemann curvature. Which now is going to be a scalar function over the slit tangent bundle, right? So we have a lot of quantities, and you can talk about geometry now. So let's move on to examples. Most simple example we can have, Riemannian matrix. Choose here your favorite metric. But remember that F is that norm, so you're thinking the norm instead of the whole inner product. So you're looking at this degree 1 homogeneous function, right? That's it. You can think of all the metrics you know, of all the results that you have from Riemannian matrix, and they will work with this Finslerian setting as well. Next, we can have Render's matrix, which is the idea that I'm going to deform this Riemannian metric with a 1 form. But for that to be positive And for the symmetric form to be positive definite, the norm of beta with respect to alpha has to be less than 1. Then you have a well-defined Render's matrix on N. There are some examples of Render's matrix that come from before the work of Renders. But Renders was a physicist that introduced this matrix with the idea that time and in space-time seems to have a preferred direction. There's a unit direction of time. And Renders argues that this unit direction should not disappear from the mathematical description of space-time. So he wants to preserve the indicatrix of the norm as a quadratic curve, but then he displaces that curve, so it's not symmetric anymore. And that's how you have Render's matrix. One of the most famous Render's matrix was actually known before him, and it was by the work of Funk. So you have this metric defined on the open unit ball. The reasons are many, but in particularly, this metric is very interesting because it's projectively flat, and it has constant flat curvature at -1/4. Projectively flat here means that your geodesics on Rn are straight lines. Next, we can have what are called squared metrics. So you can have a Render's matrix squares, then you have to divide by the metric again, basically, that's the idea. The same conditions, the norm of beta has to be less than 1. And this metrics also appear in a very natural way for not exactly. So these metrics were studied in 2008 by Professor Shen. And they have very special geometric properties. So they have some curvature properties that can be more easily classified. So they're very computable as well. And as in Renders, you already know a very famous one, which is this Berwald Metric, which is basically the Funk alpha and beta the same as the Funk metric, but in this square form, right? For this one, it is also projectively flat, and flat curvature is 0. You can also have Krapina metric. For Krapina metrics, you have to be very careful with betas. For the metric to be well defined, beta has to be nowhere vanishing on N. If it is, you're going to have these directions over your tangents bundle where the metric's not going to be regular. It's not, you're going to have these singularities on your metric, but it is possible as well. And Krapina metrics were studied by Ingarden as well in thermodynamics. So they have a relationship with Lagrangians, and you can also have generalized Krapina metrics taking powers. Next, you can have Matsumoto metrics. Again, you have alpha Riemann metric, beta 1 form. Here, interestingly, for the metric to be strong convex, the size of beta with respect to alpha, so the norm of beta with respect to alpha has to be less than half. Then this defines a Finsler metric that's known as a Matsumoto metric. And this type of metric was studied by Matsumoto in surfaces. And they were deduced from a problem. So Matsumoto wrote to Finsler, and Finsler answered him, saying a little bit about metrics and how Finsler metrics come from, instead of computing distance, if I compute time that I spend, so time light takes to travel, the time to walk on a slope of a surface, then that's not Riemannian anymore. That's Finsler metric, because the time you take to walk uphill is going to be longer than the time you take to walk downhill. And that's how these metrics were deduced and studied. Finally, you have alpha-beta metrics that were introduced by Matsumoto as a way to generalize Render's metrics. So again, we have alpha, a Riemannian metric, beta, a one form that has to be bounded. And then you have this positive infinity function that has to satisfy a certain condition for the metric to be strongly convex. And then you consider this product. So basically, if phi is simply 1 plus s, then that's going to give us the Render's matrix that we're talking about. If phi is 1 plus s squared, that gives us the square matrix that we talked about. If phi is as inverse, then you have Krupina matrix. And if phi is, sorry, I'm missing an equal sign there, is 1 minus s to -1, you have Matsumoto Metrics, right? And the interest in alpha-beta metrics is that they're computable. So calculations, because of that dependence on y, on our fundamental tensor, on the GIs, computations, every time you have a computation, you have probably the double derivatives that you would have in Riemannian geometry. And you also have products. So our calculations become very complicated very quickly. And having computable classes is something that's very interesting and very appealing in Finsler geometry. Alpha-beta metrics are one important class of those metrics. More recently, we have general alpha-beta metrics. So we have the same setting, but here V now can depend on the norm and the quotient of beta alpha. And for that metric to be well defined, we now have actually two conditions on phi, except for when n is 2 or phi is independent of b. Then you don't need the first condition, the first inequality. That's basically it. So let's, yes, and then one important example of general alpha-beta metrics that are not special alpha-beta metrics, it's already previously known as Berwald Metric, which can be defined on the upper hemisphere, or Rn, depending on how you're doing it, as this very long expression, but it is a very interesting metric that appears in very different contexts. And I'm going to say that. So now that we have a couple of examples on our heads, let's go on and talk about work products. Okay, so Berwald metrics are also projectively flat and have flat curvature 1. So we went through one special example of negative flat curvature, one of 0, and one of positive. First notion of raw work product. In the Riemannian setting, I'm thinking on G's here as the inner products. So the work product, you take two Riemannian manifolds and a positive function on M, and then you take a metric, a Riemannian metric on the product given by, it's basically G1. So P1 and P1 here are projection onto the first factor and second one. So P1 projection onto N, P2 projection onto N. And this is just the classical definition in the Riemannian setting, right? They are called Warp product by Bishop and O'Neill, but metrics in this form were studied with different names before them. So, for example, you have Krzyzkowicz, who called those semi-reducible Riemannian metrics. And within the language of Finsler geometry, I want to write that warp product as an alpha. Yes. Questions?
Yes, Patricia, sorry.
Go ahead.
There is some interpretation of warp product in Finsler case as a Finsler submersion, just like in the Riemannian case. Sorry, because I'm quite new in this area, I never checked that.
I'm gonna get there. Basically, you do have a very similar approach for the definition of Cosma, Peter, and Varga.
Oh.
But then the issue is those metrics, that class of metrics, it's not going to be very much computable. I'm gonna get there.
Okay, sorry.
No, no worry. Okay, so you can write as a square root to have the language of Finsler metric of a norm. And then the idea of Cosma, Peter, and Varga was what happens if I substitute, instead of having alpha 1 and alpha 2 being Riemannian metrics, why can't I have Finsler metrics? And they were motivated by the work of Asanov with some models for relativity using Finsler metrics and R cross M. He studied Schwarzschild metrics, or variations of the Schwarzschild metric into Finsler metrics on R cross M. So the definition is you have two Finsler manifolds and a positive function on M. Then you define the warp product in a similar form. So here, you have to be careful that F is not going to be necessarily smooth on vectors of the form. So y1 in M, y2 tangent vector in N, right? So it's going to be strictly convex. It's going to be well-defined Finsler metric on the slit bundle. So Tm0 here is that Tm minus the zero section. It's a care that you have to have in this definition. But that's okay, we can move forward. So what they did was, with this form, all those interpretations of base, manifold, and fiber, you can still have that. The formulas for curvature, depending on the curvature of N and N, you also have that. But then you have to remember that the curvatures of M and N can be already very complicated expressions. So you have something that works very similarly to the Riemannian case, but it's something that when you substitute, you're as complicated as F1 and F2 are. If you restrict yourself to, let's say, dimension 1 and 2 for M and N, then that's doable. But for dimension 3 or higher, you're already having very complicated formulas. So it is an interesting result. You have some examples in this. For example, Li and Cheng, they defined this metric with local coordinates CR theta phi in this form. If you notice here, I have a negative sign and I have no square root, and that's because I'm considering L to be x squared and a pseudo-Finsler metric. So our Hessian matrix is not going to be positive definite, but it's going to have this Lorentz signature. And this basically, if you know Schwarzschild, this is the same as the Schwarzschild metric, but instead of having the sphere, the two-dimensional sphere, you now have a Finsler metric that will have to have constant flag curvature 1. And this example is still going to be Ricci-flat, which is pretty interesting. But as I said, you have an example in the class of the first notion of work product, but all that you have that's non-Riemannian here is this two-dimensional Finsler metric, which lead us to a second notion of work product. We very much like alpha-beta metrics because they are computable, general alpha-beta metrics. So we like that idea of writing things as actual products in Finsler. So if you have a specific warping of an interval with m, where you have, let's call the coordinate of t is that idea of time. So you have time warping the metric on m, then that's a notion, a type of warping, and I can rewrite that by taking a factor of the metric alpha out. That's basically the idea. And you can do that because this expression is not going to be defined for alpha equals to 0, but then for alpha equal to 0, that's going to be a one-dimensional space on your tangent, and you can define the metric by continuity. That's the idea. And the proposal of Shen and his collaborators was to generalize this form of writing work product into a Riemannian metric times a function depending on this quotient and the coordinate t. And then for that to be a well-defined Finsler metric, so to have strict strong convexity, you're going to have a condition on phi, which is now just a function on a domain of R2. So it's much more computable. You're dealing with something that's Riemannian times a function on R2. So here, their definition. M alpha Riemannian manifold, I an open interval with coordinate t. You take that product and still call work product. As here is the quotient dt over alpha, and phi, the conditions are 2 actually on phi. So if you have those 2 conditions, the metric is well defined. In particular, if you take this alpha tilde and beta tilde, I can rewrite f in this form, which is nothing but alpha tilde, so a Riemannian metric, times a function that, if you look at, is going to depend on the norm of beta tilde, the quotient beta tilde over alpha, and that's it. So this means that this notion of work product lives inside the general alpha-beta metrics. So we already know that's going to be something computable, and it is something interesting. So in their work, some of the results that they got was to characterize when f has scalar flag curvature, meaning that the flag curvature doesn't depend on the flag, only on the pole. And this work was already improved by Liu, Mo, and Zhang. Questions? Go ahead.
Yes, Patricia. In this case, can you have, do you have still an interpretation as Finsler submersion, maybe with respect to another fiber? If you can see in the fiber R, is there some other kind of vector field such that with respect to this new vector field, this would be a Finsler submersion?
That's an excellent question that I don't know the answer to. But that's something that should be studied.
Okay.
I think.
Thank you.
Yeah.
So, terrible. Sorry.
No, it's awesome question. Thank you. Yeah. So here, in this result, I know that you're probably wondering what tau, mu, lambda, and nu are. Well, they're going to be auxiliary functions, but they can be directly expressed as phi and their derivatives. I think of order up to 4, if I'm not mistaken. And they also characterize when F has isotropic Ricci curvature, which is this equation. And again, mu, nu, and lambda, the same ones as above, right? Over their work, there are also some other results of different people already that were computing some non-Riemannian curvatures. So we have S curvature, K curvature, H curvature, a bunch of quantities that are non-Riemannian. That in the case of Peter Cosman Varga is going to be hard to compute because it's as complicated as F1 and F2. But in this case, they're a little bit easier to compute, and you can have some interesting results and theorems on that. So the paper by Liu, Mo, and Zhang goes further than just improving the result of the first theorem. So let's go to examples. If it is easier to compute, you should be able to compute examples. So let's go back to the Funk metric. The Funk metric can be represented in the form of a word product with the function written in this form. If you recall, it has constant flat curvature equals to -1/4. And then the idea of producing new examples in this way is that if I take another Riemannian metric, now alpha hat, which has Ricci curvature n-2, and I substitute alpha by alpha hat, then I produce another rock product that's now an Hessian metric with Ricci curvature -n-1/4, which is pretty interesting. In the zero case, we had the Berwald metric that can still be expressed as this word product notion. And the same trick, if I take that alpha hat and substitute, I'll also have another word product that's now Ricci-flat. And in the positive case, we had the Berwald metric that can again be expressed as a warp product in the notion of Shen and his collaborators. And with the same trick, substituting alpha by some alpha hat, you now have a word product metric that has Ricci curvature n-1. So that's pretty cool. Which leads us to what I did. And what I did was, what if you have, instead of that time coordinate, so the interval coordinate warping alpha, what if you have time being warped, right? Is the idea of a static space-time. Then, well, you can write in this form, and you have this alpha times the square root of a function depending now on x, and this quotient dt over alpha. So you could introduce a metric on this form. But in this case, your phi should be an appropriate function on an interval cross m, which might be, at first, a little bit more complicated, right? So to begin with, you want to simplify the form of this word product using spherical symmetry. So we still want to work with phi as some appropriate function on R2, so the computations are easy and doable by hand. And we were motivated by looking at the Schwarzschild metric, and specifically the Schwarzschild metric in isotropic rectangular coordinates. So this is the look of the Schwarzschild metric in isotropic coordinates. Rho here is the radius. And then if you take alpha to be the Euclidean metric on R3, Z to be this quotient, you can rewrite the Schwarzschild metric as this Riemannian metric and a function depending on rho and the quotient and the quotient dt alpha. So that's that. And that's what we did. So we're considering an R cross Rn. With these coordinates, we're gonna, so we're n plus 1 dimensional from now on. First coordinate 0, then 1 to n to the end. You have alpha times the function of z and rho, where alpha is nothing but Euclidean metric on Rn. Rho is the radius on Rn, and then z is y0 divided by the size of the alpha. Our convention is that capital Latin indices are going to range from 0 to n, and little Latin indices are going to range from 1 to n. Then we can compute the Hessian matrix. It's going to have this block form. We have these auxiliary functions, omega and lambda, that are actually the same form as in the case of Shen and his collaborators. So we can use a similar argument as they did to prove that this metric is going to be strongly convex and well-defined if and only if similar conditions hold. So in this case, omega and lambda are positive. Since we're inspired by the Schwarzschild metric, we can try to consider pseudo-Finsler metrics, and they will gonna have Lorentz signature if both are negative. So in this case, you have positive and negatives, or if omega is positive and lambda is negative. So in this case, we have negatives and positives. Then we can compute if it is either Lorentz signature or positive definite, it is invertible. We can compute directly the inverse. We can compute the spray coefficients, and you can write them with these auxiliary functions u, v, and w, which are w of degree 1 in rho, and u and v derivatives of up to order 2 in v. And then we can use Berwald's formula for the Riemann curvature to compute the trace, to compute it and finally compute the trace. So the Ricci curvature is going to be in this form. So we have this P and Q, depending on the variables z and rho, alpha squared, and this is going to be the square of the inner product between x bar and y bar, right? We can expand this a little further, and then we can write this Ricci curvature as inner product with our y bar, where P and Q can be explicitly expressed. It's not pretty, but it's not that bad for Finsler geometry. It's actually computable. In particular, it is very computable for math softwares, because you can choose n here as simply a constant. You don't have to iterate anything on a code, for example. And then the characterization that we have is for f to be Ricci-flat. So it's if and only if P and Q are both 0, if n is greater or equal than 2. So we're talking about work product on dimension 3 or higher, right? Because our manifold is dimension n plus 1. And for n equals 1, the condition is a little weaker. So we have this combination of P and Q with rho squared there. And the proof fits in the frame. So it's very easy. All the work was actually computing the Ricci curvature and having a notion that's actually computable. So the only thing we do is look at the Ricci as that inner product, and you can take this vectors that has 1 and the ith entry and zeros elsewhere. So you have a condition, and if n is greater or equal than 2, I can pick I different than j, so that one of the terms goes away, and I can get that p is 0, and now I equals j to conclude that q has to be 0 as well. And take continuity for q to be 0, for rho equal to 0. Yeah. We can compute the Riemannian case, so we can generate the Riemannian case basically to verify our computations, and they work. So in this case, P and Q have a easier form, and the components P2, P0, and Q0 are actually ODEs that are not linear but solvable by hand. And so Ricci-flat equations for n greater or equal than 2 are each of those components being 0, and by hand you can put your undergrad student to solve it. You have solutions. For n equals to 1, you have one less equation, but you still have a little bit more general solution. And you can consider Lorentz signature. The equations are going to be reduced to the same because the only difference are going to be this sign, I think, or a few signs between the components. But you can reduce the same thing. Now, the interesting thing is that it is a class that's very computable. And usually, over a class like that, assuming the format of a metric, it's enough for you to only find the trivial solution. But in this case, we can actually find non-trivial solution, even assuming the format for the metric. So if you choose a phi to generate a nth-root metric, you can compute the components of P and Q, can get the Ricci-flat equations, you can have solutions, and in the first case, it's going to be the trivial solution. But in the second, it's not. It's going to be constant on Z, but it's not on the other component, which is exciting.
Patricia, are you about to conclude?
Yes.
Okay.
So we have nth-root metrics, and then we can do the same thing. You can also consider Lorentz signature in this case. You have to be a little bit careful with the notion of pseudo metrics that you're using. And you can also generate renders metrics in this way. And it is a specific type of renders metrics, but again, a little bit of more complicated expressions, still solvable. And in the case of renders, it's not clear if you can consider Lorentz signature or not. So to finish, it's just a little bit of discussion that you have more than one notion of Ricci curvature tensor for Finsler metrics. The first one was introduced by Akbarzadeh as the Hessian. And then the vanishing of the Ricci curvature is equivalent to the vanishing of this notion of the Ricci curvature tensor. And it is that that Liu-Chen used to call Ricci-flat metrics vacuum solutions for this Finslerian field equation, right? Another notion can be given by the full tensor, so the symmetrization of the full Riemann tensor, and it was studied by Li and Shen. Their difference is going to be a non-Riemannian quantity, and we actually computed the difference of those two in the case of our solutions, and it's 0, basically. So both the solutions that we constructed, the non-trivial ones, both of them are strongly Ricci-flat metrics. So those two notions coincide and are 0. An interesting question is, there are other notions of Ricci curvatures. Are there going to be 0? Can you construct examples where one of those notions is 0 and the other is not? So it would be weakly Ricci-flat metrics. Some other problems is, as I said, construct more solutions by hand, by math software. Particularly the one for series expansions might be interesting. So you can consider this approximations metrics. And our proof for Ricci-flat theorem actually works for Ricci isotropic in a very easy way. The same proof actually works. Maybe I should have stated as Ricci isotropic instead. And you can also ask to consider a more general work product Finsler metrics. you don't have to have that warp with something one-dimensional. In both cases, Professor Shen's and my work with him. In that case, the metric produced this way is not going to be general alpha beta, but could it still be computable? And in particular, you can begin, instead of thinking of this general case of, for example, warp products in this sense for S2 cross S2, which is a very special example for geometry, right? And let me open the questions. I'll finish here because my time's up. Thank you. Questions?
Thank you. All right. Any questions for Patricia?
Actually, yes.
Go ahead.
Patricia, do you
Raise your
have?
hands if you can, please.
I think it's okay.
You did.
But
You're fine. Say everybody else.
Patricia, we have some interpretation of a heat curvature in TM using, for example, the Sasaki metric and the Churn connection. You are in TM, you have the Sasaki metric induced by Churn connection. So do you have some natural interpretation for heat curvature there? We discussed previously about this very naive idea to try to interpret in terms of this fundamental metric in with respect to geodesics. I have no clue of if this makes sense or not. It was just a very naive idea. But one question for the future would be the interpretation also in TM, maybe. So, and there was also a tip. We have this very good friend of ours, Paulo, has worked with her 2 or 3 times, Bianca Santoro. She has, do you know her?
Yeah.
Okay. So, but I remember she has made several expansions in Ricci-flat case in his PhD thesis. I don't know, but I know that they are very different worlds, but maybe it would be interesting to give a look in her PhD thesis.
Okay, thank you. Okay, yeah, that's interesting. I didn't know.
I will continue my questions later.
Okay.
But that was the two main of them.
Yeah, they're interesting questions. They're especially interesting because I don't know the answer to.
Sorry.
So, yeah, they're relevant questions. That's awesome. Yeah, thank you.
Okay. Since we're talking about Bianca, we might as well just keep talking about her. In fact, we should probably invite her for this seminar in the 2nd semester. Anyway, but
yes, good idea.
Yeah. So another thing that Bianca quite likes is sort of instantons and special geometry business. She actually wrote a little book about it. So I was interested by your non-metric versus non-torsion-free connection business. So if I understand you correctly, do those connections get induced by your choice of Finsler structure, or are they an additional structure?
They're additional. Given your Finsler metric, we can choose whichever connection you want to work with, depending on the problem. Okay,
so it's an additional degree of freedom, right? It's an additional structure you define. Okay.
Yeah.
Right. Then and these connections have curvature, right?
Yes.
Which is excellent. Now these curvatures have an L2 norm, don't they? You can use your Finsler metric to measure their L2 norm, can you not?
It is only 2.
Huh? Did you say something, Marcus? Do you know the end of my question?
Yes, I didn't understand the question.
So these connections have curvature. Curvature is a 2 tensor. By having a metric on the base manifold, Finsler or else, you can integrate the pointwise metric to get an L2 norm.
Yes.
Okay, let's call that the Yang-Mills energy, because that's what it is.
But then you have to choose which volume form you're using. So we have a choice of that as well.
A choice of what?
Of volume form.
Indeed. So let's assume I make a choice there, and I define a Yang-Mills energy subordinate to this choice.
Yes, that's possible.
Now that's a variational principle which is going to have Euler-Lagrange equation characterizing its critical points. Yeah? Meaning connections which are critical points of the Yang-Mills energy. Let's call these connections instantons because that's what they are. Now, these connections are equivalent under changes of trivialization. You know, they transform as connections. Let's call these things gauge transformations because that's their name. I want to consider connections, therefore, modulo gauge transformations because they're equivalent under gauge transformations. And I want to describe the moduli space of connections modulo gauge in this setup. Now, this is called gauge theory, and there are several questions one can ask about understanding the moduli spaces of these preferred connections. At the very first level, one can try and describe this moduli space by the linear approximation, so using the implicit function theorem to describe a neighborhood of these fellows, which are solutions to the same equation, and the rest of it. I've checked that some physicists have done the first bit of the question. They actually worked out the Euler-Lagrange equations. They did the first variation for the Yang-Mills energy, but science stops there. I believe it would be excellent to develop the Finsler gauge theory. Moreover, I've checked that so second part of the question, your supervisor, in fact, has been working behind your backs, defining a Kähler Finsler geometry, right? So he's doing a Kähler analog by reconciling the Finsler idiosyncrasy with an almost complex structure on your even-dimensional manifolds and trying to get it from there. Now, since you're interested in Ricci-flat things, then can we solve the Finsler version of the Calabi conjecture by adapting Yau's proof? Seems to me that you can. Now, if you do the second thing, you may probably publish an Inventiones and become famous, but because we don't know what's the analog of having 0 first Churn class. That's I'm telling you, the problem is this, right? We don't know what this topology, conditional on a complex topology is. But nonetheless, even working this out in some particular case or working some part of the analysis that is required to sort of generalize Yau's proof, I think that would be amazing. Writing down what's the Finsler complex Monge-Ampere equation that describes the problem would already be super interesting, and I'm very happy to work on these things. So from what you've shown, I think Finsler gauge theory and a proper approach to Finsler complex differential geometry, analytic perspective, or using analytic methods. I think these are two directions which deserve some attention from a promising young lady. I think I would be happy to cooperate on both these things. I think besides what we've already discussed, I think these two questions make sense and could lead to very interesting research lines. Also mobilizing the people from USP and the rest of it, because they understand, they've been thinking about some of these things. But I'm not insane, because your teacher has been thinking about this with his other students. So I'm not insane in this regard.